Hey everyone! So, if you wanted to measure a straight line, that's easy, right? You just grab a ruler. But what about something that curves and twists all over the place? How do you measure that? It seems almost impossible, but today we're going to pull a seriously powerful tool out of our calculus toolbox that lets us do exactly that. We're going to measure the unmeasurable.
I mean, just look at this roller coaster. How in the world would you even begin to measure the exact length of that track? You can't just lay a tape measure on it. This is precisely the kind of problem we're going to crack today, finding the exact length of a path that's constantly changing direction.
So the secret is a concept called arc length. And honestly, it's way more intuitive than it sounds. Imagine a little particle zipping along this curve. Its speed is changing from one moment to the next. So to get the total distance it went, you'd have to add up its speed at every single tiny instant along the way. And what is that process in calculus? Summing up an infinite number of tiny things. That's an integral. So arc length is literally just the integral of speed over time.
Okay, so if arc length is all about integrating speed, our first job is to figure out how to calculate that speed. We're going to be using curves defined by parametric equations, where both x and y are functions of some other variable, usually time, which we'll call t. This approach is perfect for describing motion, and we'll use it to build our formula right from the ground up.
And the foundation for all of this isn't some weird abstract formula we have to just memorize. Nope. It all starts with a very real, very physical concept that we all understand: speed. Once we know how fast something is moving at any given moment, we can work our way up to the total distance it traveled.
Now here's where it gets really cool. How do we find that speed? Well, think about it. You've got your velocity in the x direction, which is just dx over dt, and your velocity in the y direction, dy over dt. You can picture those as the two legs of a right triangle. The actual speed, then, is just the hypotenuse of that triangle. And how do we find the hypotenuse? Good old Pythagorean theorem. It's that simple.
And this is it. This is how it all comes together. We take that expression for speed we just figured out, the one from Pythagoras, and we stick it inside an integral. By integrating from our starting time alpha to our ending time beta, we're basically adding up the speed over the entire trip. And the result? The total length of the curve. This is our master formula for arc length.
So you might be wondering, why bother with this parametric version? Well, take a look at the comparison here. The standard Cartesian formula on the right can get really messy with lots of complicated fractions. But our new parametric formula? It's elegant. It's clean. It treats x and y in the exact same way, which often leads to much simpler algebra down the line, as you're about to see.
All right, so we've got our shiny new formula. But does it actually work? Let's take it for a spin on a shape we all know and love: a circle. We already know the answer for its circumference is 2 pi r, so this is the perfect test case. If we get that answer, we'll know our new tool is solid. Okay, our step-by-step process. Step 1 is always the same: find the derivatives. For a circle with radius r, the standard parametric equations are x equals r cosine t and y equals r sine t. We just take the derivative of each with respect to t. So dx dt is negative r sine t, and dy dt is r cosine t. Easy enough. Now we can find the speed.
All right, now we plug those derivatives into our speed formula. We square both terms, add them up, and look what happens. We can immediately factor out an r squared. And that leaves us with sine squared t plus cosine squared t, which is everybody's favorite trig identity. That's just 1. So the whole thing simplifies to the square root of r squared, which is just r. Turns out, a particle moving on a circle moves at a constant speed, and that speed is just the radius. How cool is that?
Okay, final step. We just need to integrate that constant speed r over one full trip around the circle, and one full revolution is from t equals 0 to 2 pi. This is probably the simplest integral you'll ever see.
So we do the integral. The integral of a constant r is just rt. We evaluate that from 0 to 2 pi, and we get 2 pi r, the exact formula for the circumference of a circle. It worked. Our formula is legit.
Okay, test drive complete. The formula works. Now, let's level up. We're going to tackle a much scarier looking curve called the cycloid. This is the path you'd get if you tracked a point on the edge of a rolling wheel. It looks super complicated, but guess what? We're going to use the exact same framework to nail this.
So yeah, these are the parametric equations for the cycloid. They definitely look a bit more intimidating than the ones for a circle, but the key here is to not get spooked. Our step-by-step process is exactly the same. We just have to trust the framework.
Step 1. Derivatives. Just like before, the derivative of x with respect to our parameter theta is r times the quantity 1 minus cosine theta. The derivative of y is just r sine theta. See? The process works no matter how complicated the equations look at first.
Now for the speed calculation. Again, we square both derivatives and add them up. This part takes a little careful algebra for sure. When we expand that first term, we're going to get a cosine squared theta, which will combine with the sine squared theta from the other term, and boom, that becomes 1, just like in the circle example. After you clean up all the terms, the whole thing beautifully simplifies down to 2r squared times the quantity 1 minus cosine theta.
Okay, now this right here, this is the crucial moment. This is a classic spot where students get stuck. We've got the square root of 1 minus cosine theta, which is a real pain to integrate. But there's a trick. The secret weapon is the half-angle identity. We can replace 1 minus cosine theta with 2 times sine squared of theta over 2. And when we do that, everything under the radical becomes a perfect square. It simplifies all the way down to just 2r times sine of theta over 2. That move unlocks the whole problem.
We're in the home stretch now. We set up our final integral for the length from 0 to 2 pi, and this integral is totally doable with a simple u substitution. We'll just let u equal theta over 2, and the rest falls into place.
So we do the u sub, we solve that integral, we plug in our bounds from 0 to 2 pi, and after all that algebra, all the trigonometry, the length of that incredibly complex curve boils down to this, 8r. Just 8r.
Just take a second to let that sink in. The length of one of those big, swooping arches is exactly 8 times the radius of the little circle that made it. That is absolutely incredible. It's the kind of beautifully simple and surprising result that makes math so amazing.
So we've seen the formula work its magic, but let's zoom out for a second and look at the big picture. Why is this tool so important? What are the key things you should really take away from all this?
I think there are 4 big things. First, we saw this deep connection between an abstract idea like length and a physical one like speed. Second, this parametric formula is just cleaner. It's more symmetrical and often easier to work with. Third, this isn't just a toy. This unlocks our ability to measure really complex, real-world curves that you'd find in physics or engineering. And maybe most importantly, we now have a foolproof, repeatable framework. Find derivatives, calculate speed, integrate. You can apply that to any parametric curve you encounter.
And this isn't just about roller coasters and weird cycloid curves. Really think about it. With this tool, what can't you measure? The orbit of a planet around the sun, the path of a highway on-ramp, the shape of a folded protein, even the length of the curve you make when you sign your own name. The power to measure the unmeasurable is now literally in your hands.